Hi, this is Austin T. This is going to be the IOT Deployment Map lab. In this lab, we'll practice designing IoT systems for different scenarios. In the scenarios, we'll explore things like distance issues, protocol compatibility, power issues, real-time monitoring. On the maps that I've created, I will list the physical, network, application, and fog and cloud layers. In scenario one, we will be monitoring home door usage. We'll create a home automation application for the front and back doors circled in red, and the intention is to track the usage of both doors over time. Here's the deployment map. As you can see, there's a lot of Wi-Fi involved, the assumption being that home Wi-Fi is now the standard in the home. Wi-Fi also cuts down in the LAN on labor for running wire. The magnetic door sensors connect to the ESP32 Wi-Fi microcontrollers. These microcontrollers act as a fog layer that processes and packages the data and sends it over to the Wi-Fi router. The router then routes that data to the home computer using MQTT protocol. I chose this protocol just to keep things simple and lightweight, as a door opening and closing does not require constant monitoring or large data packages. The computer then sends the data back to the Wi-Fi router via the green arrows, and then the Wi-Fi router sends that information over to the cloud past the edge layer. In scenario 2, small IoT sensors will be inserted into the shipments. These shipments are then transported through the red dot gateway shown on the US map. The sensors will relay accelerometer data as they pass through the red dots. The data will then go to the cloud where we can observe the data. Our sensors are off-the-shelf Lorentz sensors by IoT Factory with built-in accelerometers and batteries. Batteries should last up to 2+ months. These sensors detect if large changes in package velocity occur. We would have to also calibrate these sensors to minimize detection of the truck shifting during normal driving conditions. As the truck drives, the sensors will collect data periodically to reduce power consumption. At each red dot gateway, we utilize the nationwide 4G communication with LoRaWAN communication protocols. The sensors will dump all the data to these gateways. From the gateways, we convert to wired TCP IP and send the data to the cloud. The LoRa cloud receives data across the edge with a ready out-of-the-box API that will log time and location from our data. After this, we can choose to store data on another cloud to analyze later. Scenario 3 will monitor a water pump running, and then we will send that data to our cloud. For our system, we will most likely have grid power available to us, so we can add additional devices like a PLC, flow sensor, and radio frequency. To monitor our pump, we will use a PLC's input-output to both turn on the pump and monitor the pump if it's pushing water via the flow sensor. The PLC will then output pump status to the UART microcontroller. Microcontroller will then process and package data as a fog device to send out to the HumPro RF device. The HumPro is a 900 MHz radio frequency transceiver with frequency hopping. RF transmission was selected as ideal for this application because farmlands typically are wide open with good lines of sight. A low frequency also extends the range, and frequency hopping also adds security and avoids interference. The HumPro takes data from the microcontroller and sends it to another HumPro receiver. The receiver is wired to our main office CPU for data processing. As like before, the CPU will repackage our data into TCP IP and then send the data over to the edge to the cloud for data analytics. The CPU is really the cornerstone of our system here. It acts as our server and control. It can send data to the cloud and turn the pump on or off. Scenario 4 will be an IoT system that monitors motor RPM, motor usage, and the 3D printer usage. These metrics will be sent to the cloud. Additionally, a door chime will be connected to the cloud that is activated when a student requests access. Here is our diagram. Again, we take advantage of the existing Wi-Fi on the 802.11xxx standard. This IoT system is branched out in a cluster tree to take advantage of the multiple existing Wi-Fi APs. On the door chime and 3D printer branch, we connected with wiring as digital inputs to yet again another Wi-Fi microcontroller that acts as a fog device. On the motor branch, a Hall effect sensor connects to a VFD as an input to determine motor RPM. The VFD should also be able to monitor the motor on time and date. Again, another fog microcontroller acts as a data consolidation point. Both branches connect via Wi-Fi to two different Wi-Fi APs. These APs are hardwired to a router with the TCP/IP protocol. The router then sends data across the edge to the cloud. Some constraints I see with this design is that hardwiring up the 3D printers and getting them to communicate properly might be a little bit of a challenge. The same thing would go with the VFD. I'm not entirely sure what model we have in the lab and if it's compatible to be wired up to a microcontroller. Scenario 5 is just a simple moisture sensor hooked up to a microcontroller that connects to the ThinkSpeak cloud. So I can pull data from the microcontroller, pull the soil moisture levels, or I can send over commands to, for example, take readings only once a day or up it to 3 times a day. And yeah, it uses my established Wi-Fi and home router that's already in place. And that's about it. Cool. Thanks for watching.